In this video, I'm going to be looking at this topic, oscillations. Oscillations is an important topic in physics, whether you are talking about O-level physics or A-level physics. In O-level physics, it is called simple harmonic motion, a type of oscillatory motion. Of course, you know that oscillatory motion is a to and fro motion of a body about a fixed point. An example is a simple pendulum motion. In A-level, it is simply called oscillations. So, as I go through this video, it's going to be a kind of series, a playlist containing all the subtopics under oscillation. So I'm going to differentiate between oscillations in O level and also oscillations in A level. And I'm going to be solving some questions that apply to both O level oscillation, that is simple harmonic motion, and A level oscillation. Now, basically, you can see the definition there, a to and fro motion of a body about a fixed point. Example include a simple pendulum, a vibrating mass, and loaded test tube. And there are two types of oscillations. We have the free oscillations and also the forced oscillations. And what do you understand by free oscillation? In free oscillation, the body oscillates. The body vibrates with its own natural frequency without the application of any external forces like frictional force or resistive force acting on it. Now, it should continue indefinitely when once that body is set vibrating. Okay, for example, the natural frequency of vibration of a simple pendulum is given by 1 over 2 pi, the square root of acceleration due to gravity over the length of the pendulum. Now, that is, if I have the pendulum and I know the length, with that, I can calculate the natural frequency of that pendulum. So when once that pendulum bob is set oscillating, it should continue like that forever, as long as no resistive force acts to stop or to slow down or to dissipate the energy of the pendulum. So that is how we calculate the natural frequency. So we can see that the natural frequency depends on the location of the pendulum. Whether because if you do the same experiment on the moon surface, it gives a completely different result, different observations compared to when the experiment is done here on the Earth's surface. And it does not depend on the amplitude of oscillation. And it is clearly depends, okay, I've said that already. Now, again, you can see that in the case of forced oscillation of vibration, some external periodic forces act on the body in order for it to maintain its oscillation. We need the application of some periodic forces or impulses so that this system, this body, can maintain its oscillation. An example of forced oscillation is a set of Barton's pendulum. And then you also know that forced vibration leads to what we call resonance. Now we come to simple harmonic motion very quickly. And what is this simple harmonic motion? We say that it is a motion of a body, to and fro motion of a body about a fixed point, such that its acceleration A is directly proportional to its displacement from the fixed point and is directed towards the fixed point. So the acceleration, in fact, simple harmonic motion is defined in terms of the acceleration of the body in oscillation. You can see that now. So the acceleration is related to the displacement. Okay, so we can write this in symbol and the acceleration A is directly proportional to the displacement x. We use x to represent the displacement of the body from the fixed point, and also the acceleration is directed towards the fixed point. So this is how we define simple harmonic motion in terms of acceleration. Okay, so this tells us from this equation that the acceleration of the body must not be constant, because if the acceleration is constant, then the motion of the body is no more simple harmonic. The acceleration is meant to vary. It's meant to vary directly in proportion with the displacement. And remember, displacement is a vector as well as acceleration. So if I introduce my equal to sign in this expression, I'm going to have k times x. Usually we call k the constant of proportionality. Now k will be given as omega squared, okay? And there's a negative sign there attached to k. There's a negative sign there, rather attached to the constant of proportionality, so that we have A is given as negative omega squared times x. Okay, so this is the equation of a simple harmonic motion. For those of you that have learned differentiation in calculus, you also can write this equation using this notation. The squared x, of course, the second derivative of displacement with respect to dt squared is also acceleration. So dx squared over dt squared is the acceleration of the body. It's another expression for the acceleration is given by negative omega squared times Now we want to still look at it carefully. These two are vectors. Why the negative sign? Now the omega, first of all, is called the angular frequency of oscillation. Angular frequency of oscillation measured in radian per second. Then this is a vector quantity acceleration. It's a vector. That's our acceleration. And x is the displacement. It's also a vector quantity. So I call my x the displacement. Remember that distance is just the magnitude. It does not have a direction. The displacement has both magnitude and direction. Now, what does a negative sign imply? Negative sign indicates that the direction of A and X are not the same, that as the displacement is oppositely directed to the acceleration. So when acceleration is directed this way, displacement of the body x will be directed the other way, that is in the opposite direction. So you know that when you are dealing with vectors, in vectors, we should be able to represent vectors both in magnitude and direction. That means that vector is clearly and completely represented. So when you have a negative sign in an equation that relates two different vectors, a and x, that tells direction. It means that if this negative sign were not there, then we can always conclude that the direction of A is the same as that of the displacement. But as long as the negative sign is there, it means both vector quantities A and X are acting in the opposite direction. I'll be showing you how that is so. Now let me come back again to look at this acceleration. I mean, acceleration here is directly proportional to displacement. That means that as the displacement increases, then the displacement, as displacement increases, the acceleration should increase by a certain constant amount. The acceleration should not stay constant. If constant omega squared, if this our constant was 2, it means that when displacement increases by 1, acceleration will increase by 2 times 1. When it increases by 2, acceleration increases by 2 times 2 if my omega squared is 2. So this is how to identify a system that is moving in simple harmonic motion. The acceleration must not be constant. It must vary. It must increase as the displacement increases. But now let's come back to displacement. How do you measure the displacement of a body in simple harmonic motion? I'm going to using the instance of a pendulum, a simple pendulum. Let's say I have a pendulum bulb hanging from this point or suspended from a point here. Let's say that point is a ceiling. And let's say this is we call this point where the body or the bulb is not in motion yet. We call that the rest point or the equilibrium position. Equilibrium position. And when we say the body is in equilibrium position, it means that at this point, no external force, no net force acts on the body. The body is said to be at rest. I will call that position the rest or equilibrium position. And we always take this point as our reference. That's the reference point for measuring displacement. Displacement can be measured to the left or can be measured to the right. And these two different directions, of course, how do we represent them? We need to use a mathematical or arithmetic sign to represent direction. So now this body is at the fixed point. Of course, this point O is also called the fixed point. Though the bulb is fixed or the thread or the string is fixed at this point. By extension, this is also the fixed point. I can draw a straight line below the suspension, the bulb suspension. I can draw this straight line. Of course, the motion of the body is said to be a straight line. That's a simple harmonic motion. So this body can, if it's given a slight push in this direction, at this point, given a slight push, it moves like this, rises to a point. Let's say, the motion of the bulb does not continue like this, continues like this, and then back to the same point. If it does that, that's a circular motion. To maintain, to remain a simple harmonic motion, it must rise to a maximum point, its extreme position. And at that point, it is momentarily at rest before it swings back to this fixed point or reference point once again. So the bulb moves like this, and the displacement increases. Let's say I have this as my zero on my ruler. This may be my 1 cm mark, 2 cm mark, 3 cm mark, 4 cm mark. So that displacement increases like this to the right. So if the bulb moves to the right, I can call that positive displacement. That is to say, the direction towards the right is giving a positive sign. So when the bulb is moving to the right, that is positive. Or whether it is a displacement or velocity of acceleration, as long as it is directed towards the right, we can give that a positive sign. So when the direction of the parameter is towards the right, give that a positive, whether it is displacement, whether it's velocity, or whether it is acceleration. And when the body starts moving to the left, maybe it swings because it's going to come to this point A, rests momentarily, and then starts swinging back to point O. Now, when it gets to point O, the external force acting on it, or the resultant force on it, is zero. But because of the nature of the bulb, it continues from point O, and it rises again and gets to another extreme position, point B, on the left-hand side of the mean or equilibrium position. And again, we expect that the distance is also measured in this way because while it is moving from O to B, you can say the direction is to the left. Direction to the left this time around will be giving a negative sign. Of course, we need to find a way of representing our direction mathematically using this arithmetic sign, plus and minus. So whenever the parameter or the quantity is directed towards the right, we'll give that positive, and when it goes to the left, we'll give that the negative sign. All right, so which means I can have positive displacement plus x and negative displacement minus x. So displacement is measured starting from the mean, that's the reference, the center of oscillation, this way or this way. Now, how about acceleration? How about acceleration when the body starts shrinking between point O, point A, point B? Now, let's say the starting point of oscillation is still point O, and after a while, or maybe at this point, the body is giving a slight push. It rises, it swings to point A. Now, when it's going towards point A, the direction of motion is towards the right. But from the definition of simple harmonic motion, the acceleration of the body A is always directed towards the fixed point. Towards the fixed point means towards the center of oscillation. A, so irrespective of the position or how the body is moving, its acceleration is always directed towards the fixed point. That is the center of oscillation. So you can clearly see here that while the displacement is positive, since the ball of the bulb is moving towards the right, we can give that positive displacement. The acceleration will be given negative because it's pointing towards the left. That means A minus A is equal to omega squared times x, and therefore can bring in this equation, this negative sign to this side. That gives us negative omega squared x. Okay, that satisfies this equation for simple harmonic motion, that A is equal to negative omega squared times the displacement x. Okay, this is when the body is moving. How about the velocity of the body? The velocity of the body is also in the direction from O to A. Velocity is also directed this way, or the speed. Now, meaning that when the bulb is moving from O to A, the speed of the body is also given a positive direction. That is, the velocity is positive, you know, but the acceleration is negative and the displacement is positive. What does that imply? Because whenever a body is accelerating, we'll expect that when the speed is increasing, it means the acceleration and the speed are in the same direction. Okay, so but when the speed is in this direction, but the acceleration is the opposite direction, it means that this body ought to be slowing down. This is when this body decelerates and comes to rest momentarily at point A. So meaning that as the body moves from O to A, it moves with decreasing speed. So we'll expect the speed of the body to be maximum. The speed of the body, we expect it to be maximum at the rest or equilibrium position. We also call that the center of oscillation. The maximum at the rest position or the equilibrium position or the center of oscillation. That is where the speed is maximum. That maximum speed v, we should come to that later, is given by omega multiplied by the amplitude. I can use this uppercase letter to notify or to represent the amplitude of oscillation. So this is the expression for the maximum speed or velocity of the ball. Now, let's come back to it again. Now, this speed, as of course, is maximum at the center, which means from point O to point A, the body is decelerating. You can see the speed reducing from a maximum value at point O until at point A, the velocity of speed becomes zero at point A. And because the acceleration and velocity are acting in opposite direction, meaning that this acceleration A is more like deceleration, but in the sense of this topic, it's not actually deceleration, but it's acting as deceleration. Okay, what happens when the ball starts swinging back from A to O? In that case, you can see that the direction of motion has changed. When it swings, let me just represent it here briefly or quickly. Let's say this is the same ball at point A, is now in its motion, downward motion towards the center of oscillation point O. Motion is directed this way. The displacement too, of course, displacement is directed this way. That's your displacement x. It's always directed for the center of oscillation either to the right or to the left. Then acceleration is also directed this way. So since acceleration and velocity are having the same direction, it means that as the ball moves from A to O, it speeds up. It moves increasing speed and also becomes maximum at the center of oscillation point O. Okay, but considering acceleration and displacement, you can see that since the body is moving this way, you can see acceleration is still negative because it is pointing leftward, but displacement is pointing rightward. So the equation will still be the same. Acceleration is minus omega squared times x. So it doesn't affect, doesn't change anything about the acceleration of the body in simple harmonic motion because both of them are still in opposite direction. But in terms of velocity and acceleration, since both are in the same direction, you can see that the body's is speeding up. It moves down or towards the center of oscillation with increasing speed. What happens when it goes past point O and towards point B, somewhere here? You can see that direction of motion is this way. Displacement is directed this way. Of course, that is negative because it's moving leftward, but acceleration is always directed towards the center of oscillation, towards the center. So whether the bulb is on this side of point O or on this side of point O, acceleration is still directed towards the center of oscillation. So here you can see that A is now directed towards the right. A is giving a positive sign, is equal to omega squared. You can see that my displacement is negative because the bulb has crossed to this side of the center of oscillation. That gives you minus x. Okay, the equation still remains minus omega squared x. So anyhow you consider it, in any way, in any direction, you always see that A and x are related by this equation. There's always a negative sign here to show that the direction of acceleration is opposite to the direction of displacement. Finally, how about when the body starts coming back to point O? You can see the direction of motion is this way. The displacement is this way, okay, because on this side of the center of oscillation, and acceleration is directed this way. So since A and X are in opposite direction, it still satisfies this equation. But now motion and acceleration are having the same direction. It means the ball speeds up again. The speed increases as it goes from point B, that is the other extreme position on the other left-hand side of the ball. As it goes from that point B to point O, it speeds up. It moves down or towards point O with increasing velocity. Okay, so that's the explanation of the equation concerning or relating displacement and acceleration of a body in simple harmonic motion. Okay, we shall continue from there in next video. See you in the next video.